Okay, thank you to be here for the lecture of today. Last time, yeah, or at least I calculated these three, not only these three, but transfer function. And do you remember I told you that the presence of ds, of this disturbance, which we see as a signal, somehow characterize or let me say, justify not only the S, of course, but in any case, the disturbance is important. Is important. The reason that we need one of the reasons that we need a controller is the presence of disturbance. Not only because we have seen also last time we need nevertheless a controller even though the disturbance or what disturbed me, the disturbance is what we don't want to have, even though the disturbance is not there. Nevertheless, we need a controller to achieve our goal. Basically, do you remember I told you the goal is the form of disturbance? I mean, if I don't have a goal in my life, I'm not disturbed. I can I can sleep all the time. The goal, which is fixed by our reference, isn't a disturbance. I don't know if it makes sense, this sentence for you, but for me it makes sense. No? My goal disturbs me because I have to do something to achieve this goal. When I have let me say, another form of disturbance, illness, I have to, in any case, I have to do something against it. But also the goal in the life is disturbance because something which must be achieved. This means I will do something to compensate what the difference between the goal and what I have. And disturbance generates the difference between what I have and what I would like to obtain. If I'm not able to walk because I have a pain somewhere in my body, is of course this disturbs me. I'm not able to walk. I'm not able to achieve my goal. Therefore, we can understand very well with this stupid example, but not extremely stupid, why these two transfer function the transfer function between, let me say, disturbance and output, and goal and error in the sense the discrepancy between what I want to obtain and what I have, are the same. This makes sense now if you think about that the goal can be seen as a disturbance somehow. Tamo, you don't agree that the goal is in disturbance?
Goal is disturbance.
I am trying this now in 1 minute to show you something like an analogy between goal or the goals and disturbances.
But I understand the disturbance in that way that the disturbance distract me from my goal.
Yeah, this is true. This is totally valid what you say. But what is the analogy? The analogy is to achieve the goal. Nevertheless, I need an effort with but without disturbance. Of course, you see, if I have a disturbance, I have to do more efforts. This is bad. But in both cases, I need a controller. In the sense they are similar, because I cannot achieve the goal without a controller. Of course, if I have disturbance, I have to I have to involve, let me say, more effort. But in both cases, even with disturbance or not, I need nevertheless the controller to achieve the goal. But independent of this, look at the two transfer functions. Transfer function between disturbance and output, transfer function between goal and the discrepancy between what I want to attain and what I have. But you are right when you say, here we don't have the goal. you have just a disturbance. Here, I have just the goal and don't have the disturbance. Look, I think I calculate somewhere here. No, where is it? Here is the transfer function between goal and discrepancy or the error. Let me say error, even though error, we have to clarify what I intend. Error is what the difference between the goal and what I have. Yeah. No, let me see. Okay, this is exactly what I intend. The same. Let me see. This is with ds equals 0. I calculated this here, which is here, with d equals 0. I am looking for what I calculated. Let me see if I calculated this. Why? No, I didn't calculate. You're right. Here I didn't calculate because I didn't have a place, but probably I told you, believe me, or something like that. Or I don't know if I have in the manuscript, let me say. I calculated just one of them. Let me see. Repeat if I can show you again. Somewhere I have, but I don't know where. But the reason is if you calculate one, this, for instance, no, this one. Yeah. To calculate this is not so difficult if you apply, do you remember, if you apply the rule in the numerator, you have to put what I find as a transfer function between the input and the output. This means I don't have a transfer function, or better to say, I have a transfer function 1 between this block, this signal here is this signal here, and we can see in 1. And the denominator is exactly, it is a loop structure, which I told you last time. Yeah, I didn't have yet the calculation of this transfer function, but it's calculated using Rs equals 0. If you want, I can do. No? I do. No? So we have. Of course, if I have, as you told me now, Tamo, both goal and disturbance, I have to consider, let me say, the summation of these two contributions. I show you what I did. So we repeat a little bit also this one, because last time from home, I was not able really to do the calculation by hand because I didn't have enough place to write. Let me repeat a little bit also this one because can help to understand. Again, if I have a goal and something or somebody will disturb my goal, of course, I need more effort to achieve the goal. But also without disturbances, let me do this, because last time, I was not able to produce graphical, let me say, content. GR of S, it doesn't matter which one. GS of S is the system to be controlled. What I didn't have in the slide is this case. Please pay attention. Typically, we had considered it's a negative feedback. No? Typically, but it's not, I mean, make more sense negative because if you think of this signal as the discrepancy between the goal and what I have in my life, let me say, as an output, make more sense to consider minus. But we can conceive, nevertheless, the controller if I have a plus. Think about that plus and minus. We learned also in the school they are conventional, aspects. No? What I didn't have in the calculation for sake of brevity in the slide is this analysis. If the goal, I don't have goal in my life. Calculate what, as I told you, I put this as a transfer function, but I told you, believe me or apply the rule which we learned together. I will repeat the rule for you because it's important. You can avoid calculations. I explained the calculation for different transfer function, but I didn't put in the slide these calculations. Please notice for a given transfer function, loop, and a given, let me see, as I told you last time, let me see. Yeah. We can see here, let me come back, this is an important concept. For all possible, you remember, transfer function in the loop, we have here 3 transfer functions. The first and the last one, for the first and the last one, you can find here in the presentation all calculation. This here in the middle, I will present today because it's not there. But we can see for all possible transfer function, which I can conceive in the loop, the denominators is with the same. Very important to keep in mind this. Very important. Everything which is invariant in a structure merit to be analyzed. We will see that this characteristic, this polynomial here, or this expression, let me say this expression, characterize strongly the dynamics of the loop. Okay, let me do the calculation, and I will come back on the concept of the denominator of this transfer function. Without goal, how I can demonstrate this? Calculate means, do the demonstration, do the calculation. Look, let me call this U of S. The name here, but it's not necessarily, let me see, in order to have the, we don't have it, okay. Let me consider here plus. It doesn't matter if I consider plus or minus. What is this signal here? Is ds, is, excuse me, y of s, no? This means E of s is equal minus y of s, right? Because R of s is equal 0. If R of s is equal 0, we have this. Now, what is U of s? If you think here, U of s is this signal here, which multiply GR of S. This means, let me write so. Which multiply, let me write, or let me put minus. Right. Now, what is Y of S? This is gut, ne? Y of S is D of S plus, let me consider everything plus, ne? This signal here, which is this signal here, multiply U of S. This means, let me write. Right. Ready, no? Basically, do you remember? We have to separate or to split the equation, which we have Y on the left part and D on the right part, and then calculate the ratio. No? This means Y of S, you remember as we did many times, which multiply 1 plus. We can see on the left part Y of S, and we consider this element here on the left part. This means GR of S, which multiply GS of S equal what? D of S. Now we have exactly this expression, because I have to do the ratio. Once I have on the left everything related to Y of S, when I have on the right everything related with D of S. I think you agree, because this is the easy calculation, just to show you this calculation, which we don't have in the slide. Now, I told you this, later I will come back on the concept of this invariant denominator. Invariant denominator is extremely important. All transfer functions in the loop have the same denominator. We have to ask why that, or why probably is inside the calculations, but the meaning I will insist a little bit. Now, let me consider the example which I did last time, or before last time, anyway, the example which we know, in order to go a little bit more in depth on this disturbance here. Now I can graph for you. Again, another important concept: everything is valid if the system is linear. The system is the controller is linear. Both. Everything in the loop must be linear. Now we will go ahead with this hypothesis. And at the end, I will consider when a system is nonlinear, what we can do. Or if I want to use a nonlinear controller to control a linear system. We answered already this question in dynamical systems. You remember, sliding mode control, for instance, is one of the possible controllers. In this course, I don't know if this semester I have time to repeat sliding mode control, doesn't make much sense, but it could be interesting because sliding mode control is one of the most important controllers. How many controllers I have? Infinite up to infinite. You can dream at control. You can invent the control. It's a mathematical function. What I would like to introduce in this course, but at the end, the concept of a linearization. But not now. Go ahead with this slide. The concept of linearization is an important concept. Very often we apply in order to use the tools of this part of the tool. I can use exactly, or more or less, these tools here, or at least the transfer function, everything which we know, because we are considering basically a linear system. This means we will see how we can approximate the nonlinearity using Taylor. I would like to tell you this because you know about Taylor from math. No? Taylor expansion, Taylor approximation, you can but we will do at the end. As last time in dynamical systems, I considered almost in all course the linear system. Then I told you if the system is not linear, I presented what happens in terms of dynamics. I presented a possible controller. Here we will see because you can see a different approach. But once we have the linearized system, we can apply everything which I will tell you today to next time and until the end of the course. But I will consider the linearization, I would like to say, at the end. At the end, after the linearization, we have a transfer functions. This is or at least we can use transfer function. Okay, what you have seen before last time, or I don't remember when exactly, was this example. You remember this here? And after blah, 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 many calculations, some calculations, we obtained this signal, if I apply in a step. Do you remember here? I will upload all material which I have. No? We have a step in input. This means what is in a step? It's in a battery which starts at time 0. I would like to go a little bit in depth today on the concept 0 plus 0 minus. Do you remember I told you last time? I don't know if Benedict or Felix told you about 0 plus 0 minus. Do you remember this? 0 plus 0 minus 0 plus is an important concept in control because what happens at time 0 is something difficult to me. Last time I told you, but I was not able to do the graph. At time 0, it seems to be that I start. But really, what happens at time 0 is the big problem. Really, is the big problem. Because physically could happen many things. This means the difference between when I open, this means at time 0 minus, short before. 0 minus means basically 0 minus equals short before something happens. What is this something? Close the switch. 0 minus means something before, short before something happens. Close the switch. What is 0 plus? After, short after something happened. What is in our case the phenomenon? I close the switch. It's an extremely important point because some state, some variable could be not continuous. Some variable could be also impulse. Last time I told you that. I will tell you a little bit more in depth. But before speaking about 0 minus 0 plus, but did you hear about 0 minus 0 plus? No? It's the time between 0 minus 0 plus something happens. And the idea is to analyze this phenomenon because variables between 0 minus and 0 plus could be not continuous. And something which is not continuous for us is interesting to be analyzed because this means in terms of system theory, which is something happens relevant because we lose the continuity. It could be, could not be, or could be. Or it could be that some variables, that is a state, becomes impulsive. Which they must be analyzed in this sense because an impulse is something it could be also dangerous, not for the system. Okay, but before speaking about 0 minus or 0 plus, let me show you again this. Here we have the signal in output. The output is considered, you don't have to we have this, we upload this. We have this output here. And the output in Laplace is calculated here, assuming that the input is in a battery starting at time zero. Starting means I close the switch at time zero. Sigma. Do you remember as the definition of sigma? Sigma means zero before zero, one after zero. Again, means zero before t zero minus, one starting from zero plus. But in this case, we don't have to distinguish between zero plus and zero minus because it's something which we switch at time zero. But if you want to, we can also say in this form. Now I draw a little bit better. Let me write capitalize because in S. Again, this is a U input of T multiply sigma of T, which implies Laplace is here. Which is equals 1 divided S. No? We have seen the table, very important with sigma, where sigma of T, now in sigma, we don't need to distinguish 0 minus and 0 plus, because this is something we can, but it's not necessarily because we know when that the signal is defined in this form. At zero, otherwise means less. No? And we calculated this. It was this. We calculated the output. I don't redo the calculation. No? This was the output. I can copy because I don't have time to repeat everything. What I want to introduce today is this concept here. Let me consider a general input instead of but otherwise, well, let me consider this one. It probably is easy. I save time. How I can represent in block diagram this expression here? UC, this UC. I can calculate. So we have here 1 divided RCS plus 1, my transfer function. Here we have UC of S. And here we have two signals. D of S equals RC UC at time 0. This U is not capitalized. No? You remember, it's the initial value of U in time. No? I told you this. You remember the theorem which we discussed together. In case we have an initial. And here we have the Laplace transform of my sigma. Because do you remember, we had the input is here, in case, of course, U input of t equal 1. Do you remember this? You can see here, no? The Laplace of 1 multiplied sigma is 1 divided S. If I have a 12 voltage, we have a 12 divided S. Today, I have a student which helped me to generate this YouTube channel. No? So I communicate the address per my study. So you can look. But I will upload all material. No problem. This is the Laplace transform of our 1 in our case, no? As is written here, multiply sigma. This here is 1 divided S. No? Excuse me. One divided S. Now we can see how we can consider this disturbance in different position of the loop. I mean, if I want to control this system here, the disturbance, which is represented by the initial condition, the disturbance, which is represented by the initial condition, is an input of the system. I mean, here I will have the feedback here. Assuming that I want to control the voltage. Now we can see that this kind of disturbance must be, as this is, excuse me, V not capitalized. No? I told you here, and then this disturbance here must be represented not directly in output of the system, but in input. Here we will have the controller. Here we will have the goal. Here the feedback. This means I would like to tell you that this disturbance here, it depends which kind of disturbance I have. In this case, the disturbance must be represented in input to the system. If you look at this expression, why that? Because this is the initial condition of the system. Why the initial condition could be represented as a disturbance? Mathematically, it's quite clear. Physically, nevertheless, it's something which is not zero, could help, but could nevertheless represent something which must be overcome. It depends, of course, of the goal. I will clarify a little bit in a few minutes this. But we can understand, depending on the expression, the disturbance could be in input, could be in output. Let me see if I can find another example. But in any case, a disturbance, because as I possible to say, is an external signal or can be seen as an external signal. Look at this. No? Very important, this representation. Coming back to the question of, or the argument of Tamo. If I have both goal and disturbance, of course, I have to consider more effort because we have this contribution, the contribution of the disturbance to the output, the contribution of the disturbance to the output, independently where this is. It doesn't matter where it is. Could be here, could be here. You can at home to calculate now the effect of this disturbance on the output here. Should I do it? I do it for you. It's y. Excuse me. In this case, y is u. No, let me write exactly. UC of S divided d of S. No? If R of S equals 0, this is this block here. Let me call GS of S. Divided always the same denominator. Now we learn this. No? We can see that we have this. Please try to do at home. Try to do at home. All calculation. But we have a rule. No? Everything which I emit from this signal to this signal here, divided always the same denominator. But try to demonstrate at home. In any case, to conclude this part here, if I have goal and disturbance, here at this moment I have just a disturbance, because here I have to do more effort. Why that? Because I have to consider also this. Why this both in the numerator? If you look at the rule from here to here, if this is 0, I have these two blocks in the numerator, no? These two blocks in the numerator. The same like here. It's exactly the same. And I have to do more effort because the output is the sum of both. In which sense? This here. The effect on the output superposition principle. No? And Tamo is right when he say, but if I have the goal and I have the disturbance, it's more difficult. It is. Because we can see that the output, it depends on both. We have to reduce the effect of this, and we have to achieve the goal. In this course, in this part of the course, we will concentrate on this. We will consider D of S always here, always here. But we have seen somehow we can compensate the disturbance in the dynamical system, but I will tell you again, but just shortly about this, because I don't have time. Okay, now to conclude this, to go a little bit more in depth, this we understood that the disturbance is something which can be moved in the representation in the loop. In this case, if I have an initial condition, the disturbance is here. Disturbance is an extra signal, which must be considered. You remember, this was the calculations which we did. We upload this, which we did in case 0,5 initial condition. This is the data. Yeah. This means R multiplied C1, 0,5. If I do the back transformation, in our language, free and forced answer, blah, 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 blah. You don't need for the exam, but we know we already did this free and forced in dynamical system. Here, of course, it's a little bit connected with S, but you know that from math, no? The back transformation. Look, this was the output. Isn't a disturbance in the sense of external signal, or can be seen as an external signal, can be represented as an external signal. But of course, if you say to me, but please pay attention. This was 1, no? I didn't put, but was 1. No? We can see from it. If our goal is 1, it seems to be that this initial condition helps, or could helps, because I am close to 1. It's clear this consideration is correct. Why must be considered a disturbance? If the goal is 1, it seems to be the help. Yeah. This is valid. In fact, we are considering a disturbance in sense of the signal, but could be something which must be overcome. Yes, for instance, if this is negative. This means in general, we cannot say that's help. But as a signal, depending of the goal which I have, could help. In this sense, the concept of the disturbance in control in system theory is an external signal, but not necessarily must be overcome. In this case, if the goal is 1, I didn't put here. Well, if you want, I put it. Or if the goal is 2, if the goal is larger. I mean, in general, I can say, this is 1. I can say can help. I mean, if instead of 0, pi, I have a 1, the controller should not do anything. 1 in the capacitor, 1 in the input, controller. The goal, not do anything. But in general, is a signal, an external signal, that not necessarily help. It depends on the goal. Of course, it depends on the initial condition. In general, nevertheless, cannot say that help. This means as an external signal, the name is disturbance. In some books, they say external signal and so on. Now, look at 0 minus and 0 plus, and then we conclude this part which belong to the lecture of last time, but I was not able to. What happens before 0? In accordance with the information which I have, I have just that at time 0, the voltage is 0,5. This means I have just this information, and I can assume, but of course, it's an assumption, that at time 0 minus, we have 0,5. No information about what happened before. I know just at time 0, this is 0,5. This means short before. How short before? Epsilon before here, of course, I prolonged because otherwise I cannot represent epsilon. Is 0,5. Using this analysis, S analysis, very important to understand this. Using S analysis, I can avoid this concept of, do you remember last time I told you a priori knowledge, the voltage we know from electrotechnics that change continuously in the capacitor if the input is not impulsive. Anyway, something which is clearly more intuitive. But I can say, using this analysis, exactly this analysis, at the end, I have this function here, which started at time 0, or let me say 0 plus. We can see that the value is 0.5. This means we have a necessary and continuous function. This means continuous voltage. Let me show you what I intend with another example, which I already prepared, in order to understand better 0 minus and 0 plus. Anyway, using Laplace, very important concept, using Laplace, which is outside the time, or better to say, the time is frozen. This expression here is not in time, it's in an S. This expression here, well, let me probably look at this more general. No, this is not more general because it's always more general is here. Okay, it's too symbolic. But in any case, do you remember when I transform in S, we lose the time. But it's not totally correct. We frozen the time. This means it's as if I do a photograph of the system, considering, let me say, all time. And we can see that using this approach here, let me probably read again. It's a shame it's not the general, but we can see this is this expression here. If you analyze the unit of this expression here, is volt multiplied time. Think about this. This expression here is not volt. This is volt. This expression here is volt multiplied time. I don't know if you see it, because S, I don't know if you remember in math, is time up to -1. S is time up to -1. This is an important concept. This means this U capitalized, UC capitalized this here of S is a still abstract concept, but it's something multiplies voltage in this case, but could be current, could be, it depends on the signal which we are considering. Now I have another, that is a bit to understand why we're using the Laplace, the meaning of the Laplace. You remember in math, I already repeated here, the Laplace transform is the integral starting from 0 up to t of the function f of t, which multiply exponential function of what? Minus s of t in dt. In dt, excuse me. Yeah. Typically, we consider tau. Excuse me, the integral up to infinite. Okay, the Laplace transform of f of t, excuse me for the. It's more difficult to explain with words instead of writing. Laplace transform of f of t is the integral starting from 0 up to infinite, excuse me for the error. But it's not a big error because the integral is defined in time. This means it's the time which is going from 0 up to infinite. Should I write again the definition? This is a very important concept, as if I consider the phenomenon from 0 time up to t infinite. It's clear what I intended. I try to give a feeling about the Laplace transform, what we can do and why it's so strong.
And S is
time up to -1.
Yeah.
Time up to -1.
Then you can translate it to time. one divided by.
No, the question, good question. My consideration is, if I wonder, what is the unit of U capitalized C of S? I have to answer this. If you ask me, Paola, U C of S, in order to understand that, why the unit is important in engineering? Because with the unit, we can understand better what happens in the business. Money at euros or I don't know what hours or objects or volts or ampere. This is important to understand, not concretely. Did you agree? The unit. Something more concrete. If I say ampere is cut, if I say or euros is what? Also here we can ask me. I didn't. Probably I told you once when I introduced the Laplace, but very shortly, because basically it's the program of math. Question: you see capitalize of S. What is the unit? The unit is not voltage, it's voltage multiplied time. Why that? Because if you look at the definition of the Laplace, S is, as you taught me now, is time after mass. Now, this helps us to understand exactly why Laplace is so important. Coming back to the definition, the Laplace of f of t, Laplace transform of f of t, is integral from 0 to infinity. Before I told you from 0 to t, in the sense is not totally wrong because the integral is defined in time. Should I write? Should I write? Let me see. Because the concept of Laplace is extremely difficult because it's totally abstract. Where it is? But I have no something to write. Yeah. Erroneously, I told you t here, but it's not so wrong. It's not so wrong in the sense that the integral is defined in time. This means these two elements are in time because it's defined in time. If you remember when we do an integral, the results, an integral in time, is the unit of the function multiply the time. This we did also in high school. No? We can approximate this within the sum of everything which is inside the integral multiply delta t. You remember this? In high school, what is an integral? It's the surface and the function, and then we approximate with the stepwise constant function, which is the amplitude at each step multiplied delta t. Amplitude multiplied delta t. Just to explain quickly, we can also do better. This means the Laplace of f of t is the dimension of the Laplace of f of t is the dimension of f of t multiplied the time. Think about engineering. I have the function, I have the approximation with the stepwise constant to look at the surface. This means every amplitude multiply the step delta t, another amplitude, the first amplitude multiply the delta t, second amplitude multiply delta t. This means the amplitude multiply delta t everywhere. This means voltage multiply time, ampere multiply time. The integral give another multiply everything if the integral in time, the time. But what is the meaning? I observe the phenomenon over all time, over the physical time, per time. This does not means divided time, multiply time. From 0 up to infinite. At the beginning, I told you from 0 up to t was not totally wrong. T. which is running. This means I am considering the phenomenon in all its interval of time. And then we can see that starting from 0,5, I have a continuous function, and then this I can realize mathematically doing the back transformation of this, which I will obtain this. This implies let me conclude with another, then I have to do the go ahead with the, even though this is important. Let me clarify this with other material. I will upload everything. No, don't worry about it. Let me, and then we take a rest, but I would like to conclude this in the second block. We will go ahead with the both diagrams because I have to give you material for the examination, of course. Again of 0 minus and 0 plus. So now it's difficult, 0 minus and 0 plus. It's very told you about it, definitely. 0 minus. Again, a little bit this, and then we stop a little bit. And both diagram is known. I try to go faster. But believe me, 0 plus, 0 minus in engineering is extremely important. Now we conclude with this. Look at this. I think in electrotechnic was not so deep, 0 minus, 0 plus. But in dynamical system, I told you just shortly, here is important because 0 minus and 0 plus, we can understand in Laplace. Because as if we have a photograph over time. I'll show you now. Look at this. Again, this example. Oh, so we can speed up a little bit. Again, I will upload. Follow me, I will upload. We know everything. Please pay attention here. The question is, calculate UA in case UA, the voltage, follow me, don't write. I will upload, in which the input is the delta. Delta, do you remember the delta? I told you a lot about the delta at the beginning. We have an interesting lecture, ideal delta, practical delta, and so on. And the second case, sigma. This we already seen. We had a different value. We can see here. 1 divided RC, 1 divided RC is 0,1. Before I can consider 1 divided RC equal 1. But this is just the value of the capacitance and resistance. Very important to analyze these two cases in the concept of 0 minus, 0 plus. Why 1? Because the Laplace transform of the delta is 1. Look at the table. I think also I demonstrate or I sketch the demonstration or the demonstration in the presentation. Back transformation now. No? Very important because if we do that in time, delta is the difficult function delta in time. Because in infinite short time, the amplitude is infinite, no meaning. In Laplace at time it is 1, because I'm considering I do the photograph of the system between 0 minus and infinite, or that 0 and infinite. This is one in accordance with the definition. Do you remember the example which I did with the real delta? No? One the amplitude, one the time, one the amplitude, 0,5 the amplitude, the time, twice the amplitude, the product, the surface is always one. Look, if I do very short, if I do the back transformation of this, I have this signal here. Graphically is here. Now we can see very well here that if 0 is the initial condition, I didn't wrote, but assume that is 0. We have this u at time 0 minus is not equal u at time 0 plus. I don't know if this is visible. Come on, you see here. Assume that is 0 is, but you can say me, but if the initial condition is 0,1, if you do the calculation, we will see nevertheless that UA at time 0 min is not equal a UC at time 0 plus, because the voltage from 0,1 will spring at 0,2, because we have an input. But let me consider this example. We can see that U0 minus, UA minus is not equal UA 0 minus is not equal UA 0 plus. That we can see here. But this can be seen mathematically just in Laplace, because you float and go down. I don't know, try to do it. I will upload this, try to think about. This is important for us. Let me conclude before taking the... Now, we already did, this means I need just 30 seconds. We already did this with the step. If you do the same calculation, use the input step, I will upload, no, don't worry. I do the same calculation, the initial condition is 0. Now, of course, now we have the continuity, because we are considering a different input in the sense. Why that? Basically, because the step is the integral of the impulse. Let me go ahead. This I don't need. Let me show you this interesting question. What about the current in both cases? As I told you, 0 minus and 0 plus is already analyzed, yeah, for the voltage. But the question is different variable to be analyzed. It's not so difficult, no? Because the current is C times the derivative of the voltage, but you have the voltage. If you do the calculations in case of the delta, we can see the result, but let me show you a little bit. Let me show you a little bit the calculations. But before showing the calculation, look at the picture. We can see that the current, it seems, when we look at the calculation, is not only discontinuous. I calculate the current in case the input voltage is an impulse. It's not only discontinuous, but it's impulsive. Why that? Basically, we can understand very well, because I told you that in case the input is an input involved, the output is not continuous. This means UC0 minus not equal UC0 plus. Intuitively, if I do the derivative of this, because the current in the capacitor is the derivative of the voltage, the derivative of a function which is not continuous, in math we have seen we cannot do the derivative. It's not continuous. We say we have the left derivative, the right derivative, right? But here in electrotechnics, in control, see, you want to understand what happens between left and right. This means what happens between 0 minus and 0 plus. This was my original, why I dedicated a block on this. Because in control, it's important to understand what happens between 0 minus and 0 plus. Because look, we have an impulsive current. And this in control is important to understand because the impulsive current is destructive. Theoretically, we have infinite, theoretically, infinite amplitude. This means everything is destroyed from the control. We fail in this case. Of course, practically, deep down, impulsive. You remember I told you at the beginning of the semester that with this practical impulsive structure is something which is very short, very large, not infinite in any case. But look at these calculations. Look at this calculation. If I do the derivative of this, the key point is to do the derivative also of sigma. Do you remember? The derivative of sigma is one of the possible definitions of the delta. If you look at the first slide, delta is defined as the derivative of sigma. If you look, should I show you again? And then if you do these calculations, you can see that the derivative of sigma will appear here as a delta. And then I do some algebraic calculation, and we can see that we have this final expression in which we have a sum of sigma function, which depends on sigma, it was something which depends of delta. This means at the beginning we have a 0, then we have an impulse, and then I invert the current and go into 0 because of this minus here. The current in case of sigma, doing the same calculation but considering the output, I don't have here the graph, but we can see here. Let me see, let me graph. Yeah, I have here the graph, but the graph is easy. No? The current at time 0 is 0, no current. And then we have a discontinuous current. What is this? I show you here. I don't have it, it's a shame. Let me write here. Zero current, the circuit is open. And then so. With this amplitude, 10 up to minus 6. I don't know if you agree. Yeah? This function. Okay. Yeah, and I have it. Excuse me. Yeah. More form with the general expression RC and so on. But exactly what I did now. Concluding, in accordance with the definition, if I have a linear system, if I have an input delta, I have an output of the delta. If I have a sigma, an input, and I have an output of the sigma, we can see that I can consider the relation between this and this as the derivative. I mean, the derivative of this expression here, with respect to the time, of course, is equal to this one. Why that? Because the derivative of this input is equal to this, but just in case of linear system. This expression here, in general, it's here, which was this here in the specific case, came from the derivative of this function here. And here I did here with general R and C. With general R and C. Why this cancel? Because these two function is active just at time 0. No differences between these two. Why that? Because this expression here at time 0 is 1, and larger than 0, it's 0. And I mean, this is not 0, but is annihilated by delta. This means I can cancel this. I don't know if you see it. This expression is equal to this one. Therefore, I have this expression here, which is equivalent to this here for given value of R and C. Let me see if I forgot something, but just conceptually, this here. Yeah, why just R? Because C is here, which will multiply. Here we cannot see at the end because we have the value, but C is there. C is there. Concluding, this is a very important schema we'll upload for you. This is the definition of delta mathematically. Delta in input, Y of delta in output. If I have a linear system. Sigma of t, Y of sigma of t. If we have a linear system, in accordance with this definition, I can calculate this Y sigma starting from here, just doing the derivative. This means the derivative is passing through the input to the output. And here we have the justification of this in general. Let me see if I forgot to say something, but I don't think so. I will upload, think about this. We can see that current uptime, let me write this. Current at time 0 minus is not equal current at time 0 plus. Even though the input in voltage here was sigma. Why that? Because we have the derivative of the voltage. But this can be seen mathematically, or at least can be seen very well mathematically, passing through the Laplace. Because the Laplace frozen for the whole interval from 0 to infinity, what happens? And we can see here, assuming that the current is 0. If it's not 0, that does not matter. We have nevertheless a step. Nevertheless. Anyway, we don't have the continuities in the current. Even though the voltage is continuous. This is the voltage. But the derivative of this function here is this. Extremely important to analyze what happened between 0 minus and 0 plus. In case of impulsive input, if the voltage is impulsive, this is the current, which is impulsive. Okay, let me take rest, then we will go ahead with the Bode diagram very quickly, because and then I hope to, and I would like to repeat a little bit H and KI with the exam exercise, but I hope to conclude with the Bode diagrams. So next week we conclude with the GS of S. So we have time for the linearization, but I would like to recover a lecture, because I think we have to recover a lecture, and then we will do tutorial for the exam, as always. in February. When we have the exam, anyway, I will stop now. I will stop. I will with the knowledge on tool on Bode diagram, which I will recap. You will be able to go ahead eventually in possible project, in particular with us. Again, I will not able to cover with this recap all possible, let me say, Bode diagram structures, but for the exam should be enough to understand the concept, to show me that you understood the concept, and then for more advanced or more complex structure, of course, we can do together in bachelor, programs, bachelor thesis, I intend, or project and so on. Look, very shortly, what we need to know to recap the basic concept. Easy here. If the easiest, starting with the easiest. If the transfer function is a constant, of course, we don't need to spend much energy. Basically, we can see that y of t in time is k times u of t. Nevertheless, I use always this slide in order to introduce the concept of the dB, decibel. I think it's worthwhile to repeat also for you. You can find here at the end of the concept of the decibel. Basically, the definition. Probably you with Maren you did something more precise, but I don't have time to go really precise on the topic. But what is the decibel? You can see from this definition here. First of all, we say the magnitude. This means the norm, the amplitude. I will come back on this, on the concept of the norm of our transfer function. G, I didn't put GS, I didn't put GR, could be any kind of transfer function, but please pay attention. Calculate it at J omega. Okay, here we have just time to recap. What is this? If you remember in math, S, the variable, the complex variable, as extreme complex consequence. So today we have seen that S is time up to -1. But I hope with the introduction of today, or with the recalling of the concept, the 0 minus, 0 plus, that I do and photograph, I have a better feeling what about S. Here, S, it seems to be equal in the complex variable, in this context of the Bode diagram, equals J omega. Really, S is not only J omega. I don't know if you remember. S is sigma plus J omega. In particular, it's also not exactly mathematically correct, because I have to put sigma plus minus J omega, because complex value, if I have a complex expression, we have a expression, we have a couple of solutions. I don't know if you remember Gauss, but let me go ahead with this analysis. We don't consider sigma because sigma is the real part. I don't know if you remember. Also, I calculated also for you and back transformation of Laplace, but not with a couple of solutions. But with Benedict, probably you did the back transformation. And of course, the sigma part is related to the exponential part, the real part of the exponential function. This means it's something which characterizes the transient of the answer. Now, if sigma is equal to 0, we have just plus minus J omega. And J omega, I don't know if you remember in the back transformation, we have also here in the table, represented the component sine, cosine of the back transformation. This means something which is permanent. I will consider just plus and not minus, because in our concrete analysis, we are considering just positive frequency. Negative frequency makes sense. No, I don't know if it makes sense in the sense that I can consider clockwise, anti-clockwise rotation for the sinus, cosinus. In this sense, we have a symmetry with respect to the y-axis, but the analysis which we do is for positive frequency because if you have an asymmetry, we don't need to repeat what happens for negative omega, because negative omega could mean instead of rotating in one sense, I rotate in a different sense. Anyway, I have to calculate my transfer function at j omega, s great j omega. This means we are considering the steady state analysis. Why that? Because if you remember the Beck transformation, the sigma of S, this means S equals sigma plus minus j omega. Sigma represent or reflect the transient. This means after the transient, we are defining, or for t infinite large, or let me say for sigma equals 0, just considering sinus input, the cosinus input, and waiting, practically waiting for the steady state, we calculate the magnitude of this function. Here I will do the concrete example in order to understand. And the decibel means basically 20 logarithm is base 10. The logarithm with the base 10 of what? Of the magnitude of the transfer function. In this case, the magnitude of the transfer function is k. This depends on k, the final value. Look at this Bode diagram. We can see the amplitude is 20 logarithm of k over omega, positive omega. In this case, no change is negative omega, no? As I told you, symmetry with respect to the axis y. Look here. Here I have to add some words. If I do this phase equal minus 180, this means that this k is negative. What is the phase of j omega? It's basically the arctangent of what? Of my, I show you an example probably a little bit later. Or I have it here in order to save time. Let me see if I find. The phase, I don't know if you remember in electrotechnics, the phase of a complex number, no? The phase on a complex function in this sense, I have to calculate the arctangent of what? The arctangent of the imaginary part divided the real part. No? This means here the imaginary part is 0. This means we have two possibilities. No? The arctangent could be 0, or it could be minus 180. Yeah, I put here minus 180 because we will see a little bit more mathematically in case the real part is negative. We don't have 0, but we have minus 180. If you think about a vector, if you think about a vector with imaginary part 0, but real part negative, is oriented in the x-axis, but the negative x-axis. This means minus 180 or plus 180, but not 0. I don't know if you remember this. Minus 1. Minus 1, the real part minus 1, lies in the imaginary plane on the x, on the real axis, but in the negative part. Should I draw? It's clear what I intend. What is the phase? If it's positive, it's 0. If it's negative, it's minus 180. I try to repeat a little bit fast, but mathematically, I will be more precise in the exam. This means, I didn't told you about the sign. put in minus 180, this means this case is negative. A negative value, a real negative value, the phase of this is minus 180. If it's positive, it's 0. Now, if no, think about a complex value. Yes, a little bit more articulated because we have to do in general with a complex function. But conceptually is the same. Let me go ahead. What we need very often, we have seen also in the example until now, is in the transfer function, we can see here, characterized by, for instance, 1 divided s. It's not so very nice, we can see from here that I am considering 1 divided s multiplied t1. Yeah, we can see here. One divided t1 s. It's not very well organized. This is, I don't know if it's really the last version of this presentation, but anyway, look here. It is probably a little bit enough to invert this slide. Here we have the transfer function 1 divided t1s. No? You can see here 1 divided t1s. Now, Bode diagram of this 1 divided t1s. Look here. I calculated g of s, which was equally 1 divided t1s at s equal j omega. This means steady state practically. This means if I put an input sinus or cosine, let me say cosine or the sine, it doesn't matter what, and I'm waiting for the steady state. This means from here I have this result here. From here to here is clear what I'm doing. I multiply by j, numerator and denominator. Now, definition. Again, why I introduced this trivial thing? In order to recall the definition. Why we are losing logarithm, we clarify in a few minutes. Why don't use directly the amplitude? I need the logarithm. I show you why. We have an advantage. 20 historically, 20 is there because logarithm we clarify now the advantage of logarithm. 20 is there because originally was 10 logarithm of this transfer function, but considering power elements. And then power is something related up to 2, voltage, for instance, up to 2. And then logarithm of something up to 2 is twice logarithm. No, 20, I will tell you why 20, because it's logarithm base 20. Excuse me, 10. Why 10 log base 10? Because we will see also this 10 help in general. Originally was the ratio between power. Power is related to voltage up to 2 or current up to 2. And then log of something up to 2 is 2 times log. This is in order to have a feeling where this strange definition comes from. We will see that can help us this strange definition. I mean, in math, in engineering, when we transform, we will use some indicators, even though strange. We need to have some advantage. Otherwise, why have to use? But of course, we can do some analysis also directly using the amplitude, that is the magnitude, without considering these transformations. In some cases, it works nevertheless. But in complex case, we will see we have advantages. Look. From here to here is clear. Then I apply the definition. I will have this one. No? If you use the property, of the logarithm, logarithm of 1 is 0 for any base. Logarithm of 1 is 0. You remember? No? And then the logarithm of a divided b equals logarithm of a minus logarithm of b. Logarithm of a divided b as an argument of the logarithm independently of the base of the logarithm. This is equals logarithm of a minus logarithm of b. But logarithm of a is 0 because it's logarithm of 1. This means from here to here is clear, no? Math. From here to here. From here to here is clear. Now, I have to draw this expression in the graph of what? In the y, I have exactly the magnitude in dB, exactly this expression here. And on y, I have now my independent variable, but in particular form. Here was not necessary to clarify anything, even though y is the same here, and excuse me, omega is the same here and here. But here we have to clarify because the magnitude of j omega in decibel, if you look at this expression here, with respect to omega, is not a linear. We can see that is in a logarithmic. But why I am representing in a linear form? Probably you remember, I will recall you, before explaining, in any case, for omega equal 1 divided t1, we have the magnitude 0 because we have a logarithm of 1. We agree that at least in this point, we are able to understand why the magnitude in dB is 0. But the reason why omega, the reason why it's linear is basically related to the fact that this axis is a logarithmical axis. This means that I am considering here log of omega. This means, I show you what I intend. Oh, here now, I cannot write very well. I copy and then I switch. 1 second. I copy and then I switch. 1 second. Okay. Now, also with the sun, it's more difficult to. Did you agree that I can write this in this form? Again, using the property of the log. As I told you, logarithm A divided B equals logarithm A minus logarithm independent of the base. Logarithm A multiply B, in this case, not divided, multiply is logarithm A plus logarithm B. So minus, there are more minus. Now, it's clear for omega. Why I put 1, I don't understand. Okay, now. For omega equal T1 is implied, I already justified this. Now, if the variable which I want to consider is log of omega, I mean, if I consider, for instance, omega 1 now, omega L log equal log of omega. And I will have this. As new variable. No? Now we can see that in the new scale, we have a linear function. Which is exactly what I show you here. At least so. Because with respect, coming back, with respect to omega log, with respect to omega log, so defined in a new variable, we have a linear function we can see from here. In log. Okay. And of course, the slope is minus 20. But in accordance that omega is, or this omega here is basically a logarithmical form, and the logarithm is base 10. This means the slope is minus 20 decibel, but per decades. Decades means, how possible to say, if the base is 10, I go down 20 decibel each decade. Let me see if I can explain a little bit better. But I think it would be understandable. Huh? This I told you. Mm-hmm. Yeah. Why this is 1 divided T1, we can see. A little bit math, no? Where is now? Where I am. Probably I didn't share, I don't remember where I am. No, I shared. Yeah. When this is 0. We have omega log equal minus from here log of T1, right? I am calculating when omega, when we have 0, no? Correct. No? this imply omega log equals log of 1 divided T1, yeah? Because this minus here could be, do you remember I told you log of 1 divided T1 is minus log of T1, yeah? Now, if I use this transformation, a little bit tricky, but everything is consequent. No? I will have, if I consider this, I will have log of 1 of T1 equals log of omega. This implies omega of 1 of T1. I mean, here in this scale here, we have log of 1 of T1 with this concept, which help to understand the linearity. But of course, if I used the same omega in logarithmical scale, now we can justify this expression. Because it's omega, but calculated in logarithmical scale. This is exactly what I tried to explain with this calculation. Why this one? Yeah, this is it's relatively easy if the phase, no? If you consider that we have now just an imaginary function, is this one with minus j. Minus j is in a vector, in this case in a function, but anyway, the function is oriented on the imaginary axis, but negative. The imaginary axis is negative as the phase minus 90s. I don't know if you remember. It's the vector toward, let me say, down. But I think with Mare, you did a lot of this. Let me go ahead with this transfer function. Important for us. We have seen also today, this is one of the most important. We will see basically 2 transfer functions here, and then we will do an exam exercise, or we will proceed with the program without considering oscillations and so on, even though I think in the lecture we have also oscillations here at the end. Yeah, we have also oscillation, but I don't have time really to analyze such kind of structure. But of course, starting from this knowledge, you can do that, but we will see if you want to do project with me or bachelor thesis in this context here, we will recover this more complex analysis. Let me go ahead with this. This we have seen also today how is important this transfer function. Kp dividing 1 plus T1s, a little bit more complex than before, but not extremely complex. Do you remember this function here also today we have seen? If you consider in time, no? Exactly today we have seen, in which T1 was R multiplied C. I don't know if you remember. No? But each system at its T1, of course, here the system of first order. No? First order means a differential equation with just one state. This means a polynomial as a polynomial in the denominator of the first order. About the denominator, and next week I will insist a lot. Because do you remember, also today I told you in the loop we have the same denominator. If we have something which remains the same, we must be analyzed in detail. And then we will see that this is connected with the stability of the system. I will insist next week. But I already told you once, it depends of the position of the poles of the denominator, of the transfer function, which are the zero of the denominator, of the polynomial denominator. We will see next week. Let me go ahead. Or it could be that also today a little bit, I can tell you a little bit. Let me go ahead with the Bode diagram. Here we can see the Bode diagram. Let me see if I have something in order to speed up. Yeah, could be that I have it. Oh, I have it, I have it. So we can speed up instead of rewrite everything. Let me switch on. About that, I already told you. About the magnitude, I didn't write in the slide because, yeah, for sake of brevity. But the magnitude, you remember, this is valid everywhere. No, for each kind of complex number. This means for each kind of complex function. Here's the function extremely easy and a constant, but the magnitude is root of, I don't know if you remember, real part of the complex value or complex function plus imaginary part square, excuse me, plus imaginary part square. Therefore, this here, root of k squared plus 0 squared, because we don't have imaginary part. And then we have seen everything. In case, yeah, logarithmical, we have something like that. K is the magnitude, and the logarithm of the magnitude is this one. We have to calculate. Meaning of this analysis, I would like to repeat, is assuming that I have an input sinus in this case, we have the input u red, and we have the output k, excuse me, y, which is k multiplied u, and the sinus in input, just to understand the analysis, the harmonical analysis. We are considering just an harmonical analysis. As an input, we have, for instance, sinus. This is the first idea. Yeah, just two more in depth. As I told you, I have here something. If k is negative, it happens something like that. We have the same u. I mean, assuming u equal sine of omega t, clear. The y, the output, is not as before, k multiplies sine of omega t, but is minus k multiplies sine of omega t. Therefore, this minus 80 degrees, because the signal red with respect to blue, the difference in phase is 100 degrees. Exactly. Now, we can discuss, is it an advance or is this back? Both. You can consider both. It depends. No? But in any case, 100 degree could be, as I told you, plus 100 degree or the minus 100. Both. We don't know which is. Now, the phase, I told you, now we can see a little bit better. Do you remember imaginary divide, real arcotangent? We know that from the complex calculations. No? In any case, we have imaginary 0, because we don't have imaginary part. This means arcotangent of 0 equal 0, but could be also 100 degrees, plus 100 degrees, minus 100 degrees, as I told you. In case k positive, we have 0. In case k negative, we have a minus 100. You know, I told you before, with the words. Now I will upload this. You can refine again everything. Now, again this. Magnitude. This one, as I told you quickly. Because we can calculate exactly in accordance with the definition, real part square. I forgot square, but does not change the results. This is square. I cancel with the root. I will have this one. During the calculation, which is exactly what we have seen in the slide, I will obtain this expression which I have seen before. I will calculate it also for you, this amplitude here. If omega is in value, could be 1, could be, doesn't matter what. No? In this case, 10 up to -3. In any case, not 0, because logarithm is not defined at 0. Here, please pay attention. This means in logarithmical scale. No? So we have the linearity. Let me see. We go ahead. About that I told you. Okay. Now the idea is this one, no? This was. Yeah. Look, magnitude, very quickly. How we can calculate logarithm of this. But how I can calculate this? Okay, I can split in this form. Come on, you can see. Yeah. You can split in this form. This means logarithm of this minus 20 logarithm of the magnitude of this 1 square, the real part square, plus the imaginary part square. Now is the consideration which should be done. I copy again. We can see no differences. I mean, I called this expression magnitude in dB. I call this expression magnitude in dB. Look, why? Now we have to discuss a little bit why this form. Yeah, this form is not so difficult to be understood because we can see an asymptotical part here and another asymptotical part here. It seems to be that the real diagram is asymptotical to this line here for omega towards 0 and asymptotical to this line here for omega, this is the line, for omega infinite or toward infinite. Why that? Yeah, this calculate the explanation for this part here is here because for omega equals 0, remain this. This means omega smaller towards 0, we will converge to this value in accordance to this. Now, look the limits here. Logarithm of 1 is 0. This means this will remain. Of course, the function is complex as a function of omega. But for omega very small, we will convert to this value. This axis here, what is the value of this? Whatever you want, 0,1, 0,2, 10 up -3. And then we can calculate also this point here, placing here the value which we have in omega. For omega equal 1, for instance, is this one minus 20 log of, we can see root of 2. No? What about this? Why this axis or this line is minus 20 log of T1 omega? It's easy because for omega large, you can see for omega large toward infinite, the dominating part, excuse me, it is 1. Because a logarithm is in a monotonic function, omega larger and larger, we will have a larger element. But moreover, this element here will dominate on this. This means I can calculate this one, and what remains is this. Why that? Because we have a root of T1 omega squared. This means for omega large, we will tend to this one. Now, to draw the block diagram, the Bode diagram of this function here, very often, in particular if you don't have the MATLAB, we will use this asymptotical analysis. This means we approximate with this line and with this line until, anyway, this value here, or this asymptotical element is valid until omega 2, omega e, and this asymptotical line is also, the upper bound of the validity of this part here for omega 0 is valid until omega e, and the lower bound of the validity of this approximation is valid on, again, omega e. What is omega e? When the bows meet. And in this particular case, the difference is 3 decibel. I don't know if I have the calculation omega e here. It could be that you have in the slide. Yeah, but it's not difficult. No, it's an exercise I show you from math. When basically this element here equal Kp. This means Kp, omega Kp equal Kp divided T1. Let me see if I have it here. But omega Kp divided T1. You don't need to calculate, but just to. No, I don't have. I didn't calculate, but it's easy to do. No? Let me see to fix for you. Yeah. No, I made a small mistake because I have to consider this line here is not, equals this for omega very large, clear, as I told you before. But to calculate this, I have it here. To calculate this point, I have to consider this line which meet this line. Because far away from omega infinite is not anymore this, but exactly this. I show you the calculations. Just to you don't need just to understand. Eh? Let me see, otherwise I lose material. Here. Okay, here. Now, before that, let me do the phase, and then we will see omega e. The phase of this. The phase of the numerator minus the phase of the denominator. Do you remember this from electrotechnique? No? When we have the ratio between two complex numbers. The phase of the numerator minus the phase of the denominator. This also came yeah, from the definition, no, of the phase. We can demonstrate this. I don't know if I have the demonstration, but probably with Mare, in complex number, you did this. If this is defined as in as a ratio. I don't have time to show you, but probably you remember this. The phase of Kp is 0, if Kp is positive, this is it. And the phase of this is always arcotangent of imaginary part divided real part. This means exactly this one. Now, if I don't have the calculator, we can do the same analysis. I mean, the function is this one, the function is this one. But why directly I graph in this form? The reason is for omega towards 0, omega 0 is in this direction here, infinite, far away. Because in logarithmic scale, logarithm of 0 is infinite. In this case, minus infinite. Excuse me, infinite. This distance here is infinite. Omega towards 0 go in this direction, infinite omega. Now, for omega equals 0, the arcotangent of 0 is 0, asymptotically. For omega infinite, we'll have a minus pi divided 2 because of this minus here. I don't remember a little bit. I don't know if you remember trigonometric functions. To calculate, let me say, asymptotically, we have this line here. And from here, let me say this line here. Or in general, this is valid for omega relatively large. To calculate exactly this, of course, we need a calculator to put some points, but believe me, it's in between. If you remember a little bit the trigonometry, you understand that this is what. Yeah, ready. But MATLAB does perfectly, yeah, without approximation. But the asymptotical approximation nevertheless helps to calculate omega e. Again, omega e is when this line meets this line here. Why this? Yeah, of course, it's a little bit an approximation, of course, because really I have to put here 1 plus, no, 1 plus. That could be nevertheless yeah, no, it's correct. This is a little bit complicated to explain, but we can see from here. When this line is valid, it's valid for omega infinite. But this line for omega infinite or the relative large, I can neglect this. So I will find this line here. But of course, close to this point, I cannot neglect this. Doing these calculations, I will obtain results. Cancel this. And this 1 divided to 1. Let me see if I can justify a little bit better these calculations. Mm. I don't know if it's in the slide somewhere, there or something more, but I don't think so. But I see a mistake here. No, oof. No, this is okay here, no? Mhm. But then it's okay. This is okay, it's okay. Because it's enough that this one, the root of one is okay. It's a little bit strange, but everything is okay. Let me see if I can say something more about this. Let me finish. This I already told you. What happens now in case I don't find the last transfer function which I want to consider, and then we conclude this year. We have seen also this very, very often. Here we have an error. This is the truth. This here I have to correct. Yes, not correct. Please pay attention. Because we can see it's not the same. This is the valid. Excuse me. Here's the valid. Here it's wrong here. I mean, what is wrong here is this S here. It's probably a LaTeX error. This S here is not there. Please pay attention. This area is not there, but I have in the manuscript. Look, I will justify this now. I will justify this. I hope I have. Let me see. 1 second. Yeah, I have it. I have it. Yeah. Yeah, here is probably LaTeX and LaTeX. This S here is not there. No? Without this S is correct. Let me go ahead with the manuscript. Look. Yeah, exactly this. Extremely important for us. S again, J omega, steady state analysis. I will obtain this. No? From here, I will obtain this. Now, decibel. 20 log of this expression. 20 log of this expression means this here. Then I can use the property of the logarithmical 20 log of this expression plus 20 log of this expression in terms of amplitude. No? I can split. I didn't wrote anything, but 20 log of the product of two elements, I can split before writing. So 20 log of magnitude of Kp divided 1 j omega t multiply magnitude of 1 divided j omega. And then I apply the logarithm. I mean, from here to here is clear. No? First of all, I have to split the amplitude. The product of the amplitude of the product is the product of the amplitude. No? The amplitude of the product is the product of the amplitude. Now, we have here applying the logarithm. From here to here, how I can do 20 logarithm kp minus 20 logarithm of root of real square plus omega square t1 square minus 20 log. Why that? Because of this. No? Do you remember the amplitude or the magnitude of j omega is omega? Logarithm 1 divided j omega is basically minus log of omega. Omega is always positive. We don't need to. Okay, let me now calculate this expression. Gesundheit. For omega very small, what dominate is this part. Did you agree? Because this is 0 or 10 to 0. This 10 to infinity, plus infinity, larger than this one. This means I will obtain something that reflects this expression. For omega infinite, will dominate this and this, this and this. Why that? Because this remain constant. This is basically as before, root of omega squared t1. This means we have a 40 minus 40 log of omega, because this expression here for omega large is logarithm of omega, like this. Therefore, we sum up these two contributions. We have here asymptotically minus 40 dB. This is the attack. Phase, extremely easy to do, because the phase of the product is the product of the phase, the sum of the phase, excuse me. The phase of this is the sum of the phase. The phase of this is K, we have seen before, no? The phase of Kp minus the phase of this. And the phase of this is, we have seen both. No? The phase of one, which is 0, the phase of this, which is 90. In asymptotical form, we have seen both. We have already seen this, and we have already seen this. We have to combine now. No? If Kp is positive, the phase of Kp is 0. This means now we have both. One is asymptotically minus pi divided 2, 90 degrees, minus 90 degrees, and the other this one. This means for omega 0, we are here. And then we are going to minus p because we have to sum up. No? For this infinite we have seen before, that is pi divided 2, minus pi divided 2, we go to pi. What I forgot to say before, but it's easy to see, at this point here, 40 degrees. I mean, in the middle, between 0 and infinite, is 40 degrees. Let me see. Let me see what I can say more. Let me come back to the slide. Probably I have something in mind to tell you. Yeah, and in the manuscript was a little bit fast, but probably with Maren you calculate this 40 degree at this omega e. Now we can see here. I didn't put here the calculation because you did, at this omega e. Do you remember omega e? We calculate in the show you this. Omega e was let me see, 1 divided T1. No? Exactly this omega e. Exactly, 1 divided T1. Therefore, for omega 1 divided T1, arco tangente O1 is 40 degrees. Here is 40 degrees. Here we can do the same calculation. Is 135. We're using the same calculation. Here it's quite clear. At omega e, in the slide is very well, but very well done. I didn't do the calculation, but omega e is 1 divided T1, and omega e, we have this is not specified. It's not specified this point here, but this omega e. This point here is omega e. I didn't put any. Otherwise, it's clear. If you move toward infinity, it's not exactly in the middle. At omega e, again, what omega e is quite important. It's the point in which the two asymptotical approximations meet. Okay, I think for our program is enough. Let me sketch what we did next week. Next week, I will start a little bit with the analysis of the denominator, meaning, stability shortly, recalling a little bit some aspect of the differential equations. And then we have the last presentation, which I try to analyze how we can design the controller using a few things about the body diagram. Very important, nevertheless, to analyze the stability, because it's connected with of course, with the synthesis or design of the controller. But the controller, in any case, must guarantee the stability. And then I will come back on H, Ki, but we will conclude with the example with the exercise, also calculating the rest of the controller. What is the rest of the controller? GC, no? GC. The idea was to repeat today H and Ki, but I think we can next week in one block I will conclude this analysis of the GC, and the second block I will do an exam exercise. Then means I will reconsider H, last time I will reconsider Ki, and then we will complete the analysis with GC. Okay, today the last part was basically dedicated to the block diagram. We have 10 minutes. I didn't realize we can look a little bit to repeat this H and Ki, right? Or are you tired? Tired. Okay. Next week we conclude, and I need just one block to do. It's not much. It seems to be much, but it's not. Using this concept here to obtain the GC for a given H and a given Ki, which I assume to be calculated. But one thing I would like to show you without many effort at this moment. Let me see. Just to recall one thing. Last time The topic which I consider an example was the car, no? The parking. Oh, what was? Auto parking? You remember what I did? The auto park. Yeah, the auto park. Sure things. Look, this was the problem. I think, no? What is the picture which I show you? This is the controller. Last time, very quickly, we calculate H and Ki. H in order to obtain at least asymptotically infinite time to cover distance, I don't remember, 1 meter, I think was. And we have seen that I don't need any integrator in the control. Then, very important now, to recap. Ki is an element which states the velocity of my auto parking, because the goal is don't crash. I have to go back close to the window, to the wall, excuse me, without crashing the wall. This means the wall should be, let me say, the distance of the wall when I start the auto parking should be larger than 1 meter. If I put excuse me, the distance larger than 1 meter, if I mean, the sensor measure 1 meter 10 centimeters, sets 1 meter in order to park. H, the parameter H is responsible for this precision. We don't need H. I mean, H equals 0. Now, the second challenge is to park in the reasonable time. Because if I need 1 day to park, I cannot go down from the car. To realize this speed, we design a parameter Ki, but the Ki is designed in a steady state form. Of course, it's an approximation. I will repeat next week, but I don't know if you remember. We designed Ki considering to follow a ramp. Of course, this is not quite correct because you remember in dynamical system, in math, this kind of differential equation, they don't have a linear solution. They have an exponential solution. But as I told you, we can follow at least asymptotically. This means after some time, the ramp. Therefore, we consider Ki as a part of the steady state. But basically, the effect is in the transit. What happens now? I can speed up as I want my auto parking. The last time I told you how I can specify this Ki is, for instance, saying that I want to achieve 1 meter in 1 second. I will repeat at the end of the lecture next week. Now, but what happens? I guarantee that I reach 1 meter in 1 second with Ki. But it could happen. Now is the question extremely important aspect to discuss 1 second in order to introduce the design of. It could happen that, first of all, it's just an approximation. But anyway, approximation nevertheless could be relatively valid because we can see that we cannot achieve 1 meter in 1 second, but something more. But what we need to be respected is that the overshoot does not exceed 10 centimeters. I mean, this is a little bit an exaggeration. Huh? Look at this. I can speed up as I want. But the risk is that then I crash with the wall. Of course, at the end, I will achieve 1 meter. But look, what is the meaning of this? Like this. The meaning is, I will crash, at least mathematically, against the wall, infinite time. Crash here, crash here, crash here. Because I mean, and excuse me, the risk is I crash. I don't know what is the wall. The wall is 10 centimeter. I didn't put here 10 centimeter. But in any way, I will exceed 1 meter infinite time. What I have to guarantee is that the overshoot should be not more than 10 centimeter. I don't know if it's clear. The overshoot, the maximal error, should be not more than 10 centimeter. This will be done using GC of S. In order that I will not reduce much my velocity with which I would like to, let me say, park. The idea is to park in 1 second, to cover 1 meter in 1 second, the red line. This is not possible because the system does not react as in a linear output. We don't have the linear output, but we design as if it's a linear output. The risk that I will exceed 1 meter more than, for instance, 10 centimeter if the sensor measures 10 centimeter. This means we have to guarantee that the maximal overshoot, maximal error is not more than 10 centimeter, 0.1. And this is guaranteed by GS. Of course, I try to break a little bit the car, in the sense, or the controller will renounce at this 1 second, a little bit, we can see. And this is the task of GS. Okay, next week, in 1 block, I will finish, in any case, using an example. I have the last presentation, but it's not so extremely difficult. I will introduce, nevertheless, the concept of the denominator. And then okay. Thank you for your attention. We will see next week. We conclude, and then we will refine with the last meeting in January, and then we will do at least 1 meeting of the tutorial. We will see how is your feeling. We discuss also for the schedule next week, guys. But we have 2 lectures in January. This means we have time. It's not. Thank you.